We're Team Mandy's, and we wanted to create a robot that can make the life of someone who is visually impaired just a little easier. To do this, we came up with the design of a shoulder gadget that uses a LiDAR sensor and a camera to identify objects in front of a user and how far away they are. This gadget would then alert the user of this potential obstacle. This is our complete initial design process. First, we set up the robot calibrating to each user's specific measurements. Then we use the computer vision and LiDAR readings to detect objects. Finally, we would relay these readings to the user by giving audio feedback.
However, our team realized that this project didn't fit within our time and resource constraints and decided to scale down our idea down to 2 prototypes. Our first prototype is a robot designed for a remote-controlled car known as the MBot that uses infrared sensors to find open paths in a maze and tells the user which way to turn using 3 speakers. This incorporates the audio feedback we initially wanted our robot to provide. We started with the base template robot that was provided for us and added 3 IR sensors, and these sensors were connected to 3 speakers. The sensors and speakers are connected through a transmitter and receiver utilizing XBee modules. Finishing up the hardware, we began to code the algorithm the MBot will use to determine how to navigate through the maze. We created an algorithm that takes all of the IR sensor readings to calculate the right path by determining which direction the IR sensors detected the most open space.
We first tested the MBot without the blindfold to time how long it takes us to go through the maze. This will be used as a control for the blindfolded test. We then tested our robot by placing a blindfold on a member of our team and having them listen only to the speakers receiving directions from the MBot on how to get through the maze. We measured success based on how much time the blindfolded driver took compared to the non-blindfolded trial. Some drawbacks that resulted in our testing failing was that the speakers could only be played one at a time, which made it more difficult for the users to determine which direction to move the MBot. Another issue was that the speakers used the same sound, so it was hard to differentiate which speaker the sound was coming from. After having 3 people attempt to drive the MBot through the maze blindfolded, we determined the driving test to be a failure.
Now, this has all been within the scope of a maze in our laboratory. Our team wanted to make a gadget that could alert users of obstacles in a real-world scenario, but on a smaller scale than our initial design. And our second prototype does just that. Introducing the Wand. Our second prototype is a wand that uses a LiDAR sensor to tell a user when an obstacle is in front of them. It incorporates the LiDAR technology that we hope to use in our initial design. First, the wand uses a 1-point LiDAR sensor to measure the distance between the user and the next thing in their path. To make sure it was working, we programmed the sensor to display its values to the serial monitor. Then, we programmed our 2 vibration motors to vibrate on 3 different settings based off of the LiDAR's distance. If the distance in front of the sensor is 25 to 50 centimeters, only our small 6mm vibration motor vibrates. If the distance is 10 to 25 centimeters, only our large 10mm vibration motor vibrates. If the distance is less than 10 centimeters, then both motors are triggered. These ranges are long enough so the user has enough time to react, but not enough for the wand to constantly alert the user of obstacles in their path. To support all of these parts, we used an Arduino Uno board and a 5-volt battery and attached them to the body of the wand. Since this is a handheld gadget, we designed it with accessibility and ease of use in mind. With doing this, we were able to achieve a weight of approximately 200 grams, or less than half a pound. This is thanks to our sets of aluminum maker beams, which are light yet sturdy and able to support all of our parts. All of this together costs about $58 to make from scratch. But since our team already had access to a lot of our tools, this prototype only cost us $25. Once our wand was put together, it was time to test. We started off by testing our 3 settings and seeing if the motors vibrated as intended. Once we ensured they were functional, it was time for some real-world application. We asked a group of volunteers to put on a blindfold and try walking through a door using the wand, and our robot passed the test rather consistently. Almost every volunteer was able to use the wand's obstacle detection to avoid a wall or find a gap where they didn't feel any vibration.
That's good.
These MBOT and Wand prototypes both serve their individual purposes, but together they bring us one step closer to our goal, creating a comprehensive gadget that aids a visually impaired user in navigating the world around them.
Don't break it. Don't break your face.